Hello and welcome to this clip reviewing Group 2 chemistry but using a range of earlier topics from the first half of the first year A-level chemistry course. My aim in doing this is to help you to see that Group 2 chemistry can be used as revision of older material as opposed to something that's brand new, because quite often Group 2 chemistry is taught closer to the end of your exams. So what we're going to try and do is use the Group 2 chemistry as a context or backdrop against which we can look at older topics. So I'm talking about things like ionization energy, electronegativity and redox reactions as applied to reactions with water or oxygen, for example. And in addition, we'll have a look at some of the uses of Group 2 compounds. All Group 2 elements are metals and so have giant metallic lattices when in the solid state. So the lattices will all have delocalized electrons attracted to an ordered lattice of positive metal ions. And therefore they'll have all the same physical properties that you expect metallic lattices to have, such as conductivity of electricity, conductivity of heat, relatively high melting points, etc. So as you go down the group from beryllium to barium, the ionic and atomic radii increase due to a greater number of electron shells. So this gives rise to specific trends not only in our physical properties but also in the chemical behaviour of the elements as well. So the melting points of the metals decreases as you descend the group. The reason for this is greater shielding means weaker attraction between the nuclei of the metal ions in the lattice and the delocalized electron cloud, so less energy is required to overcome this attraction. So the melting points of the Group 2 metals are higher than Group 1 metals in the same period. So the reason here is because the charge difference between a 2+ ion and an electron is greater than the charge difference of a 1+ ion and an electron. So therefore, if you take two metals that are next to each other, e.g. in the same period, or row, more attraction will take place between metal ions and delocalized electrons in Group 2 metals for the same level of shielding, or same number of shells, so therefore more energy is needed to overcome these attractions. So in the process of reacting, all Group 2 metals will lose 2 electrons as they do so. This is in order to have a complete outer shell octet of electrons, so they form 2+ ions and lose 2 electrons. So this process of losing electrons means the metal is oxidized. This happens more easily as you go down the group from beryllium to barium. This is because the additional shielding means that the nuclear attraction for the outer shell of 2 electrons is weaker the larger the metal atom becomes. So as you go from beryllium to barium, the metal is more easily oxidized, so it becomes more reactive in the way that the equation above the arrow shows. So another byproduct of this is the fact that as you go down the group, the larger the metal atoms become, and therefore the less electronegative they become. The reasoning behind it is very similar to the reasoning behind the reactivity. It's because the additional shielding means that the nuclear attraction for the outer shell of 2 electrons is weaker the larger the metal atom becomes. So it becomes less able to attract bonded electrons along a covalent bond. So how come it's more reactive but less electronegative? This is where people sometimes get a bit confused. So because electronegativity depends on the formation of a covalent bond along which the bonded pair of electrons can be attracted, because metals react by losing electrons, as such they're not going to be very electronegative. So as you go down the group, this tendency becomes even less because of the reason in blue on the bottom right of the screen. So as the metal is more easily oxidized, which is the process of losing electrons, therefore it becomes less electronegative. So another trend is the first ionization energy decreases as you go down the group. So again, going from beryllium down to barium, the additional shielding means the nuclear attraction for the outer shell of 2 electrons is weaker the larger the metal ion becomes. So if we change the equation at the top to ionization, not forgetting of course to add our state symbols, now we're talking about a very specifically defined process, less energy is needed to lose an electron as the atom gets bigger, so it's easier to form a positively charged ion. at 1 plus charge. So if we put it in the context of how the first ionization energy is defined, less energy is needed to lose an electron from each atom in 1 mole of gaseous atoms to give 1 mole of gaseous 1 plus ions. So let's now look at some specific reactions you need to be able to remember. Luckily, most of the group 2 metals follow the same pattern, so I'm going to use M to represent my group 2 metal. So before we go any further, it's worth pointing out that beryllium is not studied at A level because it has a high charge density, meaning low number of shells but a relatively high number of protons, and this makes its chemical behaviour different to other group 2 elements. So we cover beryllium, or if you were to go on to study chemistry at university, you would look at beryllium at that point. So putting our diagram of the relative atomic or ionic radii for group 2, just as a reminder, you may recall we talked about group 2 metals and their tendency to become more easily oxidized as you go down the group. And you probably also remember this equation that we talked about a few minutes ago. So for the same reason that metals lose 2 electrons more easily as you descend the group, it makes them better reducing agents, so therefore another species can gain the electrons. That species would then be reduced. So the reaction with water is quite similar down the group. So if we take magnesium down to barium and ignore beryllium like we said, it's basically M plus H2O giving you MOH2 and hydrogen gas. So you can see from the animation the picture of calcium bubbling away there as it reacts with water. And from the still photograph you can see a steady increase in the vigorous nature of that reaction. So we can look at the redox behaviour of this reaction by applying oxidation numbers to everything, remembering that uncombined elements excuse me, are always oxidation state 0. Now metals in group 2 only lose 2 electrons, so they only ever form +2 oxidation state ions. So that's worth remembering when you're applying your oxidation state rules. So first of all, M is oxidized from 0 to +2, and 2 hydrogen atoms are unchanged in redox terms. They remain as +1. And the remaining 2 hydrogen atoms are reduced from +1 to 0. So although not all the hydrogen atoms have ended up undergoing redox change, it still means 2 of them have, so therefore this is a redox reaction overall. So in their reaction with dilute acids, it's the same overall change, 2 electrons being lost, but this time they react with 2 protons, 2 H plus ions. So the above equation represents the ionic equation for the reaction taking place whenever a metal in group 2 reacts with an acid. But the moles of acid used depend on the number of hydrogen atoms available for dissociation. So for example, sulfuric acid is H2SO4, so 1 mole of H2SO4 dissociates to give 2 moles of H+. But hydrochloric acid is HCl, which only contains 1 hydrogen atom per molecule, so therefore 1 mole of HCl only dissociates to give 1 mole of H+. So you need to be careful to make sure that you're actually reacting enough moles of acid to have 2 moles of H+ reacting. So therefore, when you create or construct an equation with a specific acid, look carefully to see how many moles of hydrogen are actually available to make sure that 2 moles of H+ are available to react with 1 mole of group 2 metal. So you may also be asked to state what you'd observe on addition of a metal to an acid. Anything that implies a gas is given off will be enough. Don't say hydrogen, as you can't actually see that it's specifically hydrogen without going and testing it with the lightest splint. So, the reaction with oxygen gas follows a similar model for all group 2 metals, and note how it's also a redox reaction if we put in the oxidation numbers. So in this case the observation would be a brilliant white flame and the production of a white powder of magnesium oxide in the example shown in the animation. And if you look at the oxidation numbers like I mentioned a second ago, again the metal is oxidized and the oxygen is reduced. So they may ask you to demonstrate using oxidation numbers why this is an oxidation reaction. So group 2 oxides, their reactions with water, is one you need to remember. And you also need to remember the solubility of the hydroxides. So the hydroxides of group 2 metals are generally not very soluble, as you can see from the state symbols and the general template for the equation. But this solubility increases as you descend the group. And because obviously if it's more soluble and it's a hydroxide, that means it can release OH minus ions into solution, so its alkalinity increases. Okay, so let's have a look at a summary of some of the reactions of group 2 metals using calcium as an example. So you'll notice there's also some reactions in here we haven't covered so far, but it shouldn't be terribly difficult to write out all the chemical equations for these reactions with the correct state symbols. So a good bit of practice might be to pause the clip and try it, and then bring in your examples to your teacher when next time you're in college, and see if they agree with you. So I'm going to finalise the group 2 sort of survey we've been doing with some uses of group 2 compounds. So most group 2 oxides, hydroxides and carbonates are bases, so this is used for specific purposes. So calcium compounds, for example, are used in agriculture to neutralise the acidity of soil for crop yields. So things like calcium oxide, calcium hydroxide, for example, you can see it in the analysis list of ingredients online, and you can see in the photograph obviously that it's spread on a large scale by a tractor. So it's driven around by the farmer and spread over the soil so that crops can be grown in more alkaline soil as opposed to more acidic soil. And magnesium hydroxide can be taken as an antacid in medicine to combat acid heartburn by neutralising excess stomach acid. And you can see a typical equation for the reaction that might take place. Not forgetting, of course, that magnesium hydroxide is a solid. It's not very soluble in water, and therefore it's mixed into a suspension, and the suspension of the bottle has to be shaken so that the solid is well mixed in with the liquid. Now, it's really important to not say milk of magnesia. It's an old style name for this particular remedy. You have to actually say magnesium hydroxide if you're answering a question about this in an exam question. Another interesting use of barium, or group 2 compounds rather, is barium sulfate. It's a very, very insoluble compound, so it's often given prior to x-rays excuse me, with food, so that when you have the x-ray done, it shows up as a brilliant white colour. So you can see obviously an x-ray of someone's digestive tract. So even though barium 2+ ions are highly toxic, if the barium sulfate is insoluble, they're not going to be released into the bloodstream. So the patient is actually safe. So let's now have a look at some group 2 practice questions. We'll only do a few, but it's worth having a look at the different ways in which they might ask about it. So the first question is fairly straightforward. They just want you to complete and balance an equation. Then it asks you to use oxidation states to show that calcium has been oxidized. So calcium has been oxidized from 0 in Ca metal to +2 in CaCl2. And because the oxidation number of calcium increases, you can call this oxidation. So moving the page down a bit, the next question says the elements of calcium and strontium in group 2 of the periodic table both react with water. They want you to name the gas produced. We looked at this reaction a bit earlier. So it's obviously hydrogen, or H2. And a balanced equation for the reaction, well, we can do this quite easily. And that gives us Sr plus 2H2O liquid, giving SrOH2 aqueous plus H2 gas. They didn't ask for the state symbols, but I thought I'd put them in anyway. So the next question asks us to explain why the student obtained different volumes of gas by reacting water with the same mass of calcium. So because strontium has a greater relative atomic mass, the same mass of strontium would have less moles than an equivalent mass of calcium. So the equivalent mass of calcium would have to give more moles of hydrogen, so a greater volume of gas. So moving the page down, then it finally asks us to predict the pH of the solutions formed. So anything between 8 and 14, because group 2 hydroxides are alkaline. So let's now move the page over to the next one. So this time it's a slightly longer answer. When barium metal is added to water, the reaction taking place is much more vigorous than with calcium. You need to explain why that's the case. So thinking back to what we talked about a bit earlier in terms of reactivity and the sizes of the atoms. So barium atoms are larger than calcium ones, and that's because barium atoms have more shielding than calcium atoms. And because shielding always outweighs the increase in nuclear charge as you go down a group, this would mean that barium atoms lose 2 electrons more easily than calcium atoms. So moving the page down a bit to the next part. Okay, so these are the remainder of the questions. The first, or the fourth rather, I should say, is asking us to use oxidation numbers to explain why the reaction involves both oxidation and reduction. So the first thing to do is assign the oxidation numbers so you can speak about it with some confidence. Or should I say, write about it with some confidence. So firstly, looking at oxygen, it changes from -2 in strontium nitrate to 0 in oxygen gas, so it's oxidized. And nitrogen changes from +5 in strontium nitrate to +4 in nitrogen dioxide, so nitrogen must be reduced. So finally it says calcium carbonate decomposes. It says write an equation including state symbols for the thermal decomposition of CaCO3. So because it's a decomposition reaction, it means you've got to split the calcium carbonate into at least 2 other things. The most obvious would be to split it into an oxide and carbon dioxide. So it's 2 marks, you can see, so therefore you have to also include the state symbols for one of those marks. And the final question, the calcium oxide reacts with water and with nitric acid, and you have to state the formula of the calcium compound formed when it reacts with each of those things. So that shouldn't be too difficult, seeing as all it really is constructing formulae from ions that we did at the beginning of the year. Okay, so hopefully this has been a reasonably useful little roundup of the chemistry of and the physical properties of group 2 elements, and also hopefully you've seen it as a review rather than new stuff you have to know. It's a review of all the different parts of the course that we taught you at the beginning of the year, but applied to group 2. So once again, thank you for your time and see you soon.